Hi guys, I recently posted this on my community section. Is this something you would be interested in? 50 likes is a new video and we have about 87 likes, which means I am bound to create a video on fine-tuning of LLMs. So in this video, let's do the fine-tuning of LLMs, but since it's a very vast topic, so I divided everything into 10 videos. This is the video number 1 of the fine-tuning series. So let's get started. We will do everything in Google Colab notebooks, and I will share this notebook at the end. And at the end, I have a special challenge for you as well. Let's try it together and we will have a winner for the challenge. Let's see if it's you or if it's me. So let's get started with the fine-tuning process. We'll understand each step one by one, try to delve deeper into the fine-tuning process, and then maybe we'll build something for MemGPT as well. So we'll talk more about that, but let's get started with the notebook here. So I have my Google Colab here and let's connect this. So before connecting, you need to change the runtime to GPU here. Okay, T4 GPU or any other GPU here. So I click on save here and then I connect. So click on connect. This is a fine-tuning example on a free, not free actually, you need to get the approval from Meta. We'll work on the Llama models and we will do 4-bit quantization. So quantization, you know, is the process of reducing the number of bits. If you have a model which is represented in 32 bits or 16 bits, you especially reduce the number of bits to 4-bit levels, and that will reduce the memory requirements because, you know, our consumers hardware is not that powerful. So we need to come up with that solution, and that solution works very fine, although we have some loss of accuracy of the models, but still the outputs are very well commendable. For fine-tuning of Llama models using 4-bit quantization, this notebook will allow you to load the Llama 7B chat HF in 4-bit, then train it using the PEFT library. PEFT is the parameter efficient fine-tuning library from the Huggingface. In layman terms, it is like you want to train a few of the parameters. So parameter efficient fine-tuning. So it's a fine-tuning process of training just a few parameters. And if you heard about LoRa, low rank adaptation, this is one of the PEFT process that you can take. And now if you have heard about QLoRa, which is quantized LoRa, so quantized, you know, it's reducing the number of representation of the bits, a 32-bit representation or a 16-bit representation in a 4-bit representation or in a lower dimensional representation. So that is the meaning of Q or QLoRa, the Q in QLoRa. We will have a look at that again in the subsequent videos, but this is just a beginning. Now let's install the libraries here. So here we have pip install bits and bytes. This is the bits and bytes library provides the 8-bit optimizer, matrix multiplication, and some quantization function that makes it easier to use with the quantized models. We need transformers. This is the library that will let you have access to different pre-trained models that we will fine-tune. Okay. Then we need the PEFT as well, the accelerate as well, and the datasets as well. So datasets will let you download datasets from your own libraries or your own created Huggingface datasets, or let you access other datasets, interesting datasets. Let us run this. So shift enter. So we let it get installed. So we're installing 5 libraries here: bits and bytes, transformers, parameter efficient fine-tuning, accelerate, and the datasets. Next, we need to install the Huggingface hub. Okay, and from the Huggingface hub we need to go to login. So we need to import this notebook login. So if I run this, we will need to give our notebook access to the Huggingface login. so that it can download different models, different pre-trained models and other things from the Huggingface hub. So let's wait for it. It's installing the Huggingface, and now we have a requirement of putting a token from the Huggingface token page. So you can just click here. You'll be taken to the access token. Now I have already logged in with my account. You need to create an account first, and then you need to create a token on the right section here, and just copy this and put it here. So let me put it here. Then click on login page. Login. So login is successful here. Now we can access the different libraries, datasets, models. Next, we are going to load a pre-trained model from Hugging Face. So here, as you can see, I have put in so much comments in each of the lines of the code so that you have a better understanding of what is going on in the process. These are all standard libraries and standard commands that you need to put, but understanding the reason behind and understanding what it does actually will help you to create better models when you try to run a huge model in the future. So we import the PyTorch. From the transformers, we import the auto tokenizer. So tokenizer, what is a tokenizer? It is a tool that is used to convert your text to numbers that the computer can understand. Then the next, we have auto model for causal LM. So when we say causal, it means it gives the output based on the history. For example, we have I am a. So we have 3 words, and using the 3 words, we will predict something. We have other methods as well, but we are using the causal method in this case. Bits and bytes config. This is used for the quantization of the model. We have a 16-bit model and a 32-bit model. Those models will not be able to be, you cannot feed it here, because you can see the GPU. This will be about 15 GB. So you cannot load a model in 15 GB. For just a calculation, I'm just showing you without quantization. If you have a 7 billion parameter model and each of the parameters is, let's say, represented by 32 bits, then you have 224 bits. Convert this to byte by dividing by 8. And you need a 28 GB of GPU to run this model with a 32-bit representation. Now, if you quantize the model and reduce the bit to 4-bit, so we divide by 8, then you just need 3.5 GB GPU to do the calculations. So that is the use of quantization here. Okay, so in summary, we need to use bits and bytes. We need to use quantization for running this fine-tuning process on a Google Colab, because we have only 15 GB GPU memory, and that is not enough for a full model to run. So we need to use quantization. Next, we use this model, which is Meta Llama's Llama 2 7 billion chat here. So I'm just going to copy this and let's paste it here. Okay, so this is the model that you need, Meta Llama. I will put in a link, or you can just search this thing on Google. And to use this model, you need to get access. So when you open this for the first time, you would see a page where you need to request the access for this model. Now I have already requested and I have been granted access to use this model. Therefore, I can add it directly here, and there is no requirement of any permission as such, because I already have the permission. But if you're running for the first time, you need to see the permission and get the permission. Okay, so then we need to put the quantization settings. So bits and bytes config. So we define this config file, and we use the bits and bytes config, the module here, and we put this 4 parameters. The load in 4-bit is true, so we are representing each bit in 4-bit. In this case, for the 7 billion parameter model, we would need about 3.5 GB of space to run this if we do this in a 4-bit. And BNB 4-bit use double quant, so that's a double quantization. It will further reduce the memory. This is the normal float 4-bit representation. We put yes, and this is the 16-bit floating point format that is used that should be used here. So we have these settings here. Then we start up the tokenizer. So auto tokenizer, if you remember, this is the auto tokenizer here. Using this module, we start up an instance of auto tokenizer, and we use this method from pre-trained. We just put in the model ID here. This will load up the tokenizer required for this model. It's a smart thing. Then we define the model. So auto model for causal LM from pre-trained, and we put up the model ID here. We put the quantization settings as the BNB configuration here, and the device map as 0. So whichever the first device that it will encounter, this code will run. So we just run this, shift enter. It will take some time for downloading and getting started. Let's wait for the model to download. So this is done. So we have downloaded the model here. So this model is a 7 billion model, parameter model. So we have model downloaded this. So this is about 10 GB and 3.5 GB file here. Next, since we have the model loaded up here in the model variable, then we set up for the training process here. We import the prepare model for k-bit training from the PEFT library. Then we enable the gradient checkpoint here, and then we prepare the model for the k-bit model. So we just run this. This will prepare the model for the k-bit training. Now we define the trainable parameters. So as we have seen, and we know, when we say PEFT, it's parameter efficient fine tuning. It means we are going to train a few parameters, but how many parameters? So in order to get a count of the parameters, this function has been created, which prints the number of trainable parameters. And you can have the percentage is also print. So let me run this and then explain. Okay, so we have not printed this out, but let's print the model. I think we have printed it here. Okay, let me run this and then let's explain this. So this is a trainable parameter is this much, and all the parameters is this much, and the trainable percentage is just 24%. Okay. It's just 0.23%. It's not even 24%, because we have trainable parameters divided by all parameters into 100. So this is just 0.23%. Okay. So what we have done is that we have used different PEFT techniques. So the technique that we have used, the PEFT technique, or the parameter efficient fine tuning technique that we have used, is LoRa. And because of that, we are able to reduce the number of parameters that needs to be trained. This is just one way of using PEFT. There are different other PEFs that you can do, but in this video, we are just using the QLoRa. So here from PEFT, we import the LoRa config here. Okay. And this is the LoRa config. So this is the rank of the decomposition. This is the scaling factor, LoRa alpha, which is 32. And these are the target modules, and these require in-depth explanation, but these are the layers of the self-attention transformer mechanism that are the targets, that are the modules, or that are the layers that we are trying to fine-tune. LoRa dropout, this again drops out different layers when running the simulation. This is a standard practice in machine learning, so that it reduces the overfitting, because machine learning has a tendency to overfit and learn the new things. So whenever you have a dropout and you remove that layer altogether, then the machine learning is more diverse and it learns from different aspects, and it prevents the overfitting. We don't have any bias here, and task type is causal LM. So causal, what I already mentioned, you have these words and you need to predict the next word. So other type of methods that I mentioned here is sequence to sequence, or sequence classification, tokens classification, and different types of tasks you can have. But for the large language models and the specific case that we are tuning in, the Llama model here, we're going to need the causal LM. Then the model we pass in through the get PEFT model. So we pass the model here and this configuration file, and then we get the LoRa fine-tuning. Okay, a model which can be fine-tuned on the LoRa principle. So we get this model. Then we print the number of parameters we have seen, which is 0.23%. It's very less. Okay, I hope this is clear, and let me explain this also. This is the trainable parameter. We set this to 0. All parameters set this to 0, and for this underscore param in the model.named parameters, then we just add in all the parameters. So all parameters is equal to all parameters plus param.numeral, or just number of elements. If param.required grad is true, then we add this to the trainable parameters. So in this way you get only just 0.23% of the parameters are need to be trained. Next, we set up the data. So on what data you're going to fine-tune the model. Okay, so you need some data that you're going to fine-tune on. Now we are going to use this airbait English codes. So you can just copy this and have a look at the data. So let me see, this is the data set, but what I'm saying is that you can create your own data set and put it in your own profile. So you click on new data set and put it in your own profile and use that data set, that is your personal data set, and fine-tune on that process. Okay, so we load the data set here. This is a standard, and this is a lambda function. It's a very smart way and a short way of defining a function and putting it all together. So we have this data here, and we define this tokenizer. It's already defined actually. So we put in the tokenizer from the samples to code. So we have the data, and we use the code part of the data, and we run the tokenizer. You see here we have this. So we tokenize this data. So whatever is available here on the code's side, we tokenize that. Okay, now it's time to train. So how do we train it? We need to define some parameters. So we import the transformers. So the next way is we define the tokenizer.pat token. So here in the pat token, we define this as the end of sequence token. So whenever we see a token or pat token, that will mean the end of sequence token. This is especially true for this Llama model, particular Llama model that we are discussing. Next, we define this trainer. That's a transformer dot trainer. So we have from this library, we have a class here, and this we are using to load in this variable trainer. We put in the model. If you remember, what is the model here? The model is this PEFT model. So this is the LoRa fine-tune ready model. So this model is ready for fine-tuning. And then we have the data set. So we use the data.train part of that. We have these arguments now. So transformer.training arguments. So these are the training arguments. So per device train batch size is 1. Gradient accumulation step is 4. Warm-up steps. You can read through the descriptions that I've written here. I will share this collab in my GitHub. Max steps, learning rate is 2 e to the power minus 4. We have the floating point 16 is true. Logging step. So each of the steps you'll see the output, and the output directory is output. So we will have a directory here, outputs. And optimization is the name of the optimizer here. That is the Paged Adams 8-bit. Then we have the collator, data collator. We collate all the data, and then we use this model.config. So we don't have any cache, but the main thing is this line trainer.train. We just start the training process. So we just pressed shift enter to load up the training process. Okay, data is not defined. So we load this data set here. It is going to download the data set. I think this is done. Now let's train the model. Now it should be available. So it is going to load up everything and do the training. So here you can see we have put the max steps as 10. So it will just do for 10 steps. But if you have time And this is just an example, but I am going to come up with the challenge in just a few minutes. So this is done. So just 10 steps. Training loss is 2.1 and training runtime is 58, and it's just okay. So this is done, and let's do some inferencing now. So we run this from transformer. We import the text streamer, so this is going to stream the data, and this we load up the model on the evaluation mode. This, it drops some of the modules like dropout and a batch norm to make the model more deterministic. And these are different things, and I will come up with a detailed video on these aspects. But let's try to stream this. Now here we need to put in the user prompt and all the settings here. So what we have done here is we have defined a function on a stream. This is going to use the user prompt, and it's going to run the stream, call the model, and do the inferencing. So runtime flag is CUDA 0, which means CUDA 0, it means it will run on the first GPU device which is available. This is a system prompt. You are a helpful assistant that provides accurate and concise responses. This is the special token markers for the beginning of instruction and the end of instruction. So we are going to use these markers, instruct inst and /inst. This is the system special marker token. So beginning of system and the end of system. So we have these sys and the /sys. This is the prompt, and we are going to use this prompt. So you can see we initially have beginning of instruction, then beginning of system prompt here, then we put the system prompt dot here because we have this system prompt, we put it here. Then we have the end of system prompt. So this is a system prompt. We have the user prompt, which we will put in here. Then we strip any leading spaces, any spaces. Then we put in the end of instruction prompt. So this is the whole instruction. Then we load up the tokenizer for this prompt. We convert it into the PyTorch tensor, and we set this to runtime flag, which is CUDA 0. It will run on the first GPU device which is available. So we load up this streamer, it's text streamer and tokenizer. Okay. So we generate the output using these configurations. We also have the generation config. So generation config, we need to define a separate generation config JSON file. So let me copy this and let me go here and make a new file. Okay. Put in this name, and inside the JSON file, I'm gonna put this. Okay, let's see, this much. So we'll load this up here, Control S, and then you can close this. So we need to have this generation config as well. Now if we run this, okay, this is done. Then we just stream it. So Shift Enter. Give me a report comparing an apple and a mango. Certainly, here is a report comparing a mango and an apple. So apple is type fruit, color red, green or yellow, shape spherical or slightly oval, sizes varies, skin, flavor, texture, crunchy and firm, nutritional value, growing conditions, requires cooler. This is a very detailed answer. Now once you have this training fine-tuned model, we are going to push it to Hub. So this is an interesting thing that you can do. You can push your models to Hub. So let's get started with pushing this model to Hub. Let's go to my Huggingface profile. Where is my profile? So here we have this profile, and I have these models here. So I am going to say dash v1 here and dash v1 here. Okay, so here I am going to change this to prompt engineer, base model name. The base model name was, it's already model ID. So you can see the model ID was here. Where is that? The model ID is this, Llama to 7 billion chat. Okay, so that is the model ID. And where is that? Okay, so we take the model base model name here. So we put prompt 48, base model name, finetune adapters v1. So if you run this, we just created two variables, adapter model and the new model. So adapter model are the changes or the fine-tuning steps, additional things that you have done on the base model. So the changes that you have done on the base model, we are calling that the adapter model, and the new model will be a combination of the adapter model and the base model. Okay, so here if we run this, we save the model, the adapter model, we push to hub, and then we say model.push to hub, we save the adapter model. Okay, so if you head back to this and refresh this, we can see that the adapters has been saved here. If you go and click and go to files, we can see that the adapters is 33.6 MB only. So these are the adapters or the changes on top of the original model that you have done. So these are just the changes that we have saved. Next, we are going to reload the base model here. So we click here to run this. Then we are going to reload the base model. We are going to load the model. Okay, we are going to load the model, this model, with the model that is the base model and the adapter model as well. So we are going to combine with this step. So when you run model is equal to model dot merge and unload, then what happens is that this model hosts the base model as well as the changes that we have done on the adapter model. So it changes everything, merges everything and put it in the model. Now once it is put it in the model, we can push to hub in the new model. Okay, what is the new model? The new model is this, finetune v1. So we push this model. I'm going to run this as well. So after we merge this model here, we are going to push the model as a new model here. This will appear here. So let's wait. While this is running, I would like to summarize again. Initially, we created two variables, adapter model and the new model. The adapter model hosts the changes that we have done on top of the base model, and the new model will host the combined things, the base model and the adapter model. So initially we pushed the adapter model, which is this model here. We already have this model. Then we load up the original model and then we merge everything into this model variable. And now we are pushing this model to the new model. So once we run this model.push to hub the new model, we can see that we have this new model uploaded. So if you go to the new model, go to the files, and you can see that this is the model about 4.94 GB and these three files, the pickle files. So this is how you fine tune a model. Now I hope everything is clear. Let me minimize everything for you and then you will be able to summarize it again. So first we install the required libraries. We load the pre-trained model here. We set up the model for training. We set up the fine-tuning data. Then we train. We did some inferencing. It's working. We push the model to hub. This is done. Now let's go to the challenge. The challenge is that you need to create something for the MemGPT. So we have MemGPT. If you go to this local LLMs, we go here. And if you go to this location, we have this. So here we have these models which are working for MemGPT, which is Ouroboros or Zephyr, Dolphin models. But let's create another model for the MemGPT function. And for the MemGPT to work, for these models to work, it has to have the function calling abilities. So one of the examples of the function that I'm going to show you is this. So I put this function here, and for you I have said beautify this, show me in a beautiful way. So this is the function. For example, user says can you help me generate an anagram of the word listen? So anagram anagram means that you can change the sequence of the words, the letters in the words, and you will get a different word. For example, silent here. So assistant says this is a function call. The name of the function is generate anagram, and the argument is the and these are the arguments. The word is the listen. Okay, and the function response is this: anagram is silent. So assistant response, the anagram of the word listen is silent. So these are some of the examples. That's amazing. Can you give me an anagram of the word race? Care. Thank you. And can you give me the anagram of the word table? Bleed. So this is one of the examples of the JSON file. So you need to create a JSON file, the same structure that we have created. So this is just one example. You need to create more such examples. You can use ChatGPT or any other libraries or data sets that you get from the web. You need to fetch those data, put it in a JSON file. You need to have at least like 50,000, 50K or 100K of these functions. And then you're going to use this JSON file to train the large language models. You can use any of the large language models. For a start, you can use smaller models which can run in Google Colab. But if you need more memory, you need to use run pods for that. In the next video, I will show how to do this with run pod. You can set up instances and you have the different capabilities and a huge GPU here. You can also create multiple instances, and therefore you can train the model better here, a larger model. So once you have this model, then you'll be able to create a model something like Dolphin here, or Zephyr 7B, or Ouroboros. That's a huge model that has function calling abilities. Now once you have function calling abilities, you can integrate into your own MemGPT. So this is the challenge. Let's create this model and let's see who can do this better. And we would also test the different models that you have created. Share me your profile of the Huggingface, and we will download the model. We will do some inference and find the best model that is possible for the MemGPT. So this is the challenge. I hope you got a pretty good understanding of what a fine-tuning is and how to do the fine-tuning process using a Google Colab. This is free. I will share this notebook, but if you need something huge, a good project, a big project, you need to use some sort of run pods or any other GPU, cloud GPU service providers. Now, having said that, this brings to the end of this video number 1 of the 10 videos. Now, I'm not going to push the second video tomorrow, because I will work on other I will work on other projects that is going on in my sequence. So let's test this out. Please test this notebook out, and if you have any problems, just comment and I will be there. I'm also available on Discord at prompt engineer 48. You can ping me up at any time. I'm also available, especially in all the comments. I'm available. Also, I would like to thank my viewers for the 4K subscribers. Now this is just a new channel, just 6.5 months, I think 7 months old, and the channel is monetized now. I have put up a post where I really thank each and every viewer of this channel, and now I feel that I'm more responsible to bring you the awesome content. You can also join the membership here, and I really dislike to self-promote, but if you want, you can join the membership here. I promise that I will bring interesting contents in the future as well. Having said that, this brings to the end of this video. Please watch out the other videos that I have on my channel, and have a nice day. Thank you so much.